Good afternoon, everybody, and thanks for taking the time to come out and participate with us for Civil Division's technical seminar. My name is Ian Cox. I'm the President-elect of APET, and I'm very grateful that you all are able to join us. Today's lecture from the Honorable Tony Gibbs is on the effects of wind on structures with examples from the Caribbean. But before we begin, I'd like to just take a couple of minutes to tell you about Engineer Gibbs, who has been with us and contributing in the Caribbean landscape for a very long time. Engineer Gibbs is originally from Grenada. He is a distinguished Caribbean civil engineer renowned for his pioneering work in designing buildings resilient to natural hazards such as hurricanes and earthquakes. Educated at Queen's University Belfast and the University of Leeds, he has led over 1,600 building projects across the Caribbean over a 35-year career. He played a pivotal role in developing the Caribbean Uniform Building Code and has held prominent positions in international engineering organizations. His contributions have earned him numerous accolades, including the Lewis Kent Award and the UN Sasakawa Award for Disaster Reduction. So joining us today, he's going to be sharing some of that knowledge. And what I wanted to also point out to those witnessing today is that he is one of APET's longest standing members at 60 years of membership. And I would like to commend Engineer Gibbs for participating in APET for that extended period of time, and we look forward to his continued contribution with us. So without any further delay, I'll turn the presentation over to Engineer Gibbs, who will lead us in this presentation on the effects of wind on structures. And I would also like to remind persons that to ensure that your full name is shown on your screen. Thank you very much. Engineer Gibbs, over to you.
Thank you, Ian. Good afternoon, colleagues. I'm pleased to have been given the opportunity to give this lecture. A few months ago, I did give a lecture on the wind hazard, and now I'm going to talk about the effects of that hazard on structures. Engineers design structures for wind forces. And in order to determine the design wind speed, we usually start with what codes or standards documents call the basic wind speed. And that basic wind speed needs to be adjusted for 5 parameters: topography, ground roughness, height above ground, the size of the structure, and the desired level of safety in order to obtain the design wind speed. First of all, let's look at topography. The Caribbean islands exhibit significant topographic effects. And in the 1980s, as part of the development of the Caribbean Uniform Building Code, we carried out a wind tunnel test on the island of Nevis to demonstrate how topography affects wind speeds. So there you can see at a scale of 1 to 3,000, the island of Nevis in the wind tunnel, one of the 2 wind tunnels at the University of Western Ontario. That university is now called Western University, but the official name is still the University of Western Ontario. Western University is a marketing title. That study is summarized in this cartoon. And in this cartoon, we look at the effects of topography on 4 different parts of Nevis. In the diagram, 100 represents what is known as the gradient wind speed. It's the wind speed so high above the surface of the earth and the ocean that is not affected by topography or by the roughness of the ocean. So as the hurricane approaches Nevis on the left-hand side of the diagram, the gradient wind is 100 units, and at 10-meter height, it's 80 units, 80% of the gradient wind. It comes ashore on the windward coast, and that windward coast is rougher than the ocean, and the gradient wind is still 100, but the wind at a 10-meter height has now dropped to 60% of the gradient wind. At Nevis Peak, it accelerates from 60% of the gradient wind to 120% of the gradient wind. And on the leeward side, sheltered by the mountains, the wind speed at the 10-meter height has dropped to 40% of the gradient wind. Now, wind forces are determined by the square to 40 on the leeward side. That's a factor of 3 in wind speed and a factor of 9 in wind forces. So the effect of topography on wind forces is very significant. When Hurricane George in 1998 passed through the spine of Puerto Rico, we were able to get a lot of measurements of the wind speeds in different parts of Puerto Rico, because there are a lot of what are known as ASOS instruments installed in Puerto Rico. So what you're seeing there are the contours of Puerto Rico with the white lines. The dashed line, which is the path of the Hurricane George, and the different colors represent the relative wind speeds. And you can see to the right side of the path, north of the dashed line, that the colors are darker than the south. And that's because the wind speeds in any hurricane tend to be stronger on the right side of the path than on the left side of the path. But also, you can also see darker colors where the topography is higher in Puerto Rico. In our wind loading standards, we do have guidance as to how to deal with the topographic effect. In the very popular American Society of Civil Engineers Standard 7, there are diagrams such as illustrated in this slide, which provide the indications of how to adjust wind speeds for topography. The numbers are not in my slide, but the numbers are in the document ASCE 7, which are readily available to engineers online. The next parameter we have to deal with is ground roughness. And that tends to be affected separately from topography, depending on the density of the buildup of the environment. So the ground roughness, what you're seeing on this diagram are idealized profiles, which in some cases are logarithmic curves. In other cases, they use different equations to get those curves. So they are power curves or logarithmic, and they both give very similar results. But these are idealized. You can see on the left, the ground roughness 1, which is over the smooth ocean. Then you come ashore, ground roughness 2 is in open fields, such as, for example, the former Caroni sugar fields in Trinidad, would be ground roughness 2. And then ground roughness 3 would be suburban domestic homes. And ground roughness 4 would be downtown Port-of-Spain, where you have the government campus and the taller buildings and the more dense developments in Port-of-Spain. So these are different ground roughnesses which have different profiles of how the wind speed grows from the ground through various heights up to the gradient wind. So those are idealized. Now, in recent decades, we have been dropping what are known as dropsons instruments through eye walls of hurricanes to determine what are the real profiles as you go from the ground, or in the case of dropsons, from the ocean to the height where the aeroplanes fly. We do not drop dropsons over land. We only drop them when the hurricane is over the ocean. So these are real indications from instrumental measurements of the effects of height above the ocean on wind speeds. Quite different from the idealized curves you've seen before. But you can't easily work with the reality in doing your calculations. So we do use the idealized curves. These are dropsonde wind profiles from Hurricane George in 1998, and these are from Hurricane Ivan in Cayman in 2004. Again, it's quite far removed from the idealized curves you saw 2 slides ago. We now have to deal with height above ground and the size of the structure. And in what is commonly known as the CCEO, Council of Caribbean Engineering Organization's document, Wind Loads for Structural Design, there's a table which combines both height above ground and size of structure. Height above ground measured in meters is the left-hand column. Size of structure, we just deal with 3 different sizes, A, B, and C. So A, B, and C occur in the 4 other columns in this particular slide. A being components, very small elements. B are small buildings, and C are large buildings. So this is what we dealt with in 1970 Wind Loads for Structural Design, and we retained this table in the 1981 newer edition of Wind Loads for Structural Design. Let's talk about size. Size does matter. The effect of size on dynamic response to gusts. The smaller the size, the greater the effect of the gusts. In this case, the gust is illustrated by waves, and the size is illustrated by different sizes of ocean-going boats. So if you have a very large ship, very large tanker, it hardly recognizes the ripples in the ocean. You go to a smaller fishing vessel, or large fishing vessel, I would say, and that is represented by SS structure, and they have a greater effect by the waves. When you get to a small fishing vessel, it's like the cladding on a building, and the waves have an even greater effect. And if you have a canoe, a very small structure in the ocean, a canoe, it's greatly affected by the waves, and we call that the fastening. So you go from foundations on the left, overall structure, to the cladding of the structure, and to the fastening of that cladding. The smaller the element, the greater the effect of the gusts. And this actually is recognized in ASCE 7 in diagrams such as this, where it adjusts the wind pressures depending on the size of the element under consideration. Item 5 is a desired level of safety. Not all of our facilities need to be equally safe. So typically, temporary structures and farm buildings, like what covers our chickens in poultry farms, are given the lowest standard of safety. The majority of buildings in the community, the vast majority, are given the next standard of safety up. And then our critical facilities, such as our referral hospitals, have an even higher level of safety than our domestic homes. And at the top of the line are facilities which, if they fail, would cause significant loss of life, like chemical plants and oil refineries. So the desired level of safety is adjusted depending on the kind of facility. The map you're seeing in this diagram is a map of load factors. Velocity for 700-year return period divided by velocity for 50-year return period of the wind, all squared, is in fact the load factor. And what we have found, what has been determined in recent decades by various researchers, is that that load factor varies with distance from the equator in the North Atlantic. As you get closer to the equator, the load factor increases. This is a very serious matter. And we have been underestimating load factors for islands in the Caribbean closer to the equator for many years, islands such as Trinidad and Tobago. So the load factor increases as you move from Cuba in the north or Bahamas in the even further north down to Trinidad in the south. This effect has actually been known to different people in different ways for quite a while. I myself, it was brought to my attention in 1971 when I met Norris Helliwell, then the head of the British Meteorological Office, and he saw our 1970 edition of Wind Loads for Structural Design, which had straight lines. You can see in the bottom diagram, those straight lines represented what we had in the 1970 edition. He looked at it and said, that's not correct. That may be correct for Europe, but not for the Caribbean. And he sent me those curved dashed lines which occurred in our 1981 revised edition of Wind Loads for Structural Design. But he didn't explain the characteristic clearly to me. He told me what I should do, but didn't tell me why I should do it. In 1997, Chris Gertz, working for a research institution in the Netherlands, determined wind loads for structural design for the Dutch islands in the Caribbean. And he produced the map, not very clear, but the top left-hand corner, which shows something quite remarkable to me. What it said was the ABC Islands, Aruba, Bonaire, and Curacao, very close to the equator, and which did not experience hurricanes at all frequently, had the potential of even stronger hurricanes than Miami for very long return periods. I know Chris Gertz personally, but he never really explained to me how he came up with that curious characteristic. It took Peter Vickery, much later, in his 2008 study for the Caribbean, which was done at the request of the Pan American Health Organization, to explain clearly what was happening. So Helliwell in 1971, Gertz in 1997, and Vickery in 2008 all came up with the same conclusion, that rare hurricanes divided by frequent hurricanes, the wind speed from rare hurricanes divided by the wind speed from frequent hurricanes, that ratio increases with closeness to the equator. And that has a significant impact on what we should be doing in Trinidad and Tobago. This is Vickery's diagram, which he produced in 2008, and he did a revision to the wind hazards in 2019, and he's retired now, but still a fairly young man. Why they retire, I don't know. But he's felt he's done enough, so he's enjoying himself now. So let's go to wind flow around structures. We can't see the wind, but if we put fumes or put effectively, if you put things in a wind tunnel, we can get visualizations of what happens as wind impacts on buildings. So these diagrams are just to give you a general picture of the flow of wind around, in this particular case, high-rise buildings. In this particular case, if the high-rise building has an obstruction upwind of it. In this particular case, if it has large openings at the base of the building, where you have an acceleration of wind speeds in that location. This is a conventional industrial building with a portal frame building. And what you're seeing here is a lot of turbulence on the leeward roof slope and turbulence on the leeward face of the building as well. In this particular diagram, it illustrates that if you have roof overhangs on the windward side, you have the uplift suctions, and under the eaves, you have the pressures. So those are particularly onersome forces added together for overhangs to resist. Buildings usually are not in isolation, and buildings upstream of your building will affect the wind flow around your building. Of course, we can't determine for perpetuity what the environment upstream of your building and all sides of your building are going to be, but it's useful to have some idea of what it could be. In Melbourne, Australia, every new building downtown Melbourne, Australia, as part of the planning process, has to be subjected to wind tunnel tests to determine how that new building will affect the existing buildings and how that new building would affect the ground level wind speeds for pedestrians in the vicinity of that building. That's a requirement, planning requirement in Melbourne, Australia, and no doubt in some other parts of the world. So adjacent buildings do affect the flow around your building under investigation. Let's look at pressure distributions. When the Sydney Opera House was being designed, wind tunnel tests on buildings were done in aeronautical wind tunnels which were designed to determine what happens to aeroplanes, typically aeroplanes high above the ground. So there were smooth flow aeronautical wind tunnels. I was actually working for Wolf Arup and Partners in London when they were doing the structural design for Sydney Opera House. So in my old age, in 2025, as one of my bucket list items, I'm going to see the Sydney Opera House in December this year. It's a long trip. Okay, so the Sydney Opera House was tested in a smooth flow wind tunnel. What happened after that was that some young researchers, led by Professor Alan Davenport, who died of complications to Parkinson's disease in 2009, Alan Davenport and other people like Professor Chermak in Colorado decided that testing buildings in smooth flow wind tunnels was not realistic. And they developed boundary layer wind tunnel laboratories. And one of the most famous and groundbreaking ones was the boundary layer wind tunnel laboratory at the University of Western Ontario. And Davenport was in the forefront of that kind of research. He was one of the most famous and much loved wind engineers of the 20th century. I was fortunate to know him well. He was my mentor, and almost everything that I know about wind engineering, I learned from Professor Alan Davenport. This is a picture in his wind tunnel at the University of Western Ontario. And what you see in the foreground is a model of Port of Spain. The red arrow, is pointing at the building which is being investigated in this particular experiment. That's the Ministry of Education building. And it was tested to determine the pressures on the glazing for that building. That was one of the purposes. Also for the loads, the horizontal loads from wind on that building. And thirdly, from the effects of that building on pedestrian comfort at ground level on the pavements. So this particular picture, a close-up of the turntable in the wind tunnel, you can see on the upper left, Nicholas Tower, on the upper right, the twin towers of the Central Bank and the Ministry of Finance, and in the middle, in a cream color, the model being tested, the model of the Ministry of Education Social Development building. The bottom left-hand corner of the slide, you can see a photograph of the completed building. So let's look at some pressure coefficients on different shapes of buildings. This is a simple rectangular high-rise building. It has 4 surfaces. The windward surface has positive pressures. All of the other it has actually 5 surfaces. It has 4 walls and a roof. So the windward wall has positive pressure. The other 4 surfaces, the sides, the leeward wall, and the flat roof, all have negative pressures or suctions. What you'd also see is that the leeward wall, the pressures are very even from top to bottom, whereas on the windward wall, it varies significantly with the height above ground. In this portal frame building, you have the windward wall with pressures varying with height above ground, the leeward wall with fairly even amount, similar pressures from top to bottom. The windward roof can have either positive or negative pressures depending on the slope of the roof, but the leeward roof is always a negative, always a suction. In this building, again, you see the windward wall with the varying pressures and the leeward wall with the even pressures. In this industrial building, there are 2 diagrams. The upper diagram is a situation where you have positive internal pressures, and in the lower diagram, you have negative internal pressures. So the internal pressures are the same throughout the inside of the building, but the external pressures or suctions vary depending on the shape of the building. And the two are algebraically added to give you the forces for which you must actually design the cladding. If you look at that same building with the wind parallel to the edge on the pitched roof industrial building, and this particular diagram is showing the pressure distribution with internal positive pressure. Now, there are ways of reducing the wind pressures and wind forces on buildings. There are things you can do. In the case of roof geometries, an increased slope would lead to a reduction in the pressures up to a point. So wind slopes between 20 and 30 degrees are favorable. Hip roof geometries are safer than gable roof geometries. A lot of experiments have been done on this. The one that I'm familiar with was done in the 1980s as an MSc thesis, also at the University of Western Ontario. And the results were interesting. And the results indicated that actually the average pressures for hip roofs and gable roofs are similar. However, the pressures are more evenly distributed over a hip roof than over a gable roof. And also, interestingly enough, one of the reasons why hip roofs are safer in hurricanes is that they require better quality carpenters to make them. If you use parapets for lightweight roofs, you reduce the pressures. And you should avoid monoslope or flat geometries for lightweight roofs. You use simple rectangular or round plan shapes as indicated in the bottom right-hand diagram. That's favorable. And if you can ensure that the natural frequency of your structure is greater than 1 hertz then you can avoid the detrimental effects of galloping and resonance. More about that towards the end of my talk. So let's look at some examples of the effects on structures in the Caribbean. Commonly, the roofs suffer the most. Lightweight roofs suffer the most. This is from Hurricane Gilbert in Jamaica. When the Queen Elizabeth II visited Barbados in October 1985, she did not have to compete with Marilyn Monroe because the dressmakers for royalty know that wind lifts things up. So her skirts had sewn into the hems little bags of lead shot to keep the skirts down. So I'm sorry about that. We have no idea the shape of Queen Elizabeth II's thighs. In Montserrat in 1989, there was a major Hurricane Hugo. It took off 2/3 of the roof sheeting for the hospital, which, by the way, was designed in Trinidad. But the rest of the building was secure. And those roof sheetings were held on in the manner illustrated in this photograph. I took these photographs 4 days after Hugo. So many of the sheets were still intact. So I was able to take this photograph. And I was also able to collect bags of failed connections. And you will see that some of them failed in direct tension. These are 7mm diameter aluminium bolts. And for them to fail in direct tension, I calculated that the upward wind pressures on the roof sheeting was approximately 150 pounds per square foot, quite significant. I gave one of my bags of those failed connections to the Civil Engineering Department at St. Augustine so they could carry out some experiments on them, but they never got back to me. If they did carry out the experiments, I never saw the results. When you go to a place devastated by a hurricane, you usually relearn existing lessons. Sometimes you learn new lessons. And this was new. For me, this was brand new. I've never seen a failure of the longitudinal splitting of timber rafters in a hurricane. I saw it in 1989 in Montserrat, and 3 years later, I saw it in the Bahamas for Hurricane Andrew. And in 2004, I saw it again in Grenada for Hurricane Ivan. And in all those cases, what initiated the failure was a form of fixing of the rafters, which I would have thought was very safe. There were drill holes through the rafter at the eaves point and thread a reinforcing rod through those holes and encase the whole thing in the ring beam. But those holes drilled through the rafters was the initiation of the horizontal failure of those rafters. So what seemed to be a very safe fastening system turned out to be not at all safe. And I've seen that happen in Montserrat, in Bahamas, in Grenada, and no doubt we'll see it again the next time we go to a hurricane-devastated country. People think that it's only earthquakes that destroy masonry, but wind destroys unreinforced masonry, as you can see here in David in Dominica. People think that if you employ top-class architects and engineers, you are ipso facto safe. Not so. This hospital in Jamaica was designed by the firm Architects Collaborative, Walter Gropius's firm. Walter Gropius was one of the most famous architects of the 20th century. He's a German of Bauhaus fame, and he had a firm in Massachusetts, Architects Collaborative. They designed the Cornwall Regional Hospital near Montego Bay in Jamaica, which the wards had to be evacuated during Gilbert because the windows blew out. Industrial buildings in Dominica. This 19th century church must have gone through several hurricanes in Antigua. Antigua is in the hurricane alley of the Caribbean. So this 19th century church must have seen and experienced many hurricanes in its almost 200-year history. However, the problem in 1995 Hurricane Luis was it impacted on a church which was riddled, where the structures were riddled with termites, and where maintenance had not been carried out for decades. So the lack of maintenance was the culprit in the destruction of this church. You can't say the same for this Princess Margaret Hospital in Jamaica. You don't want your hospital to look like that after a hurricane. Because after a hurricane, the hospital is even more greatly needed by the community than before the hurricane. This school never opened. It was a brand new school, and in September 1995, just before the school year started, it was destroyed by Hurricane Luis. Trinidad used to have a large oil industry. And at one stage, Texaco Refinery was one of the 4 largest oil refineries in the world. But the largest oil refinery in the world in 1989 was the Hess oil refinery in the United States Virgin Island of St. Croix. And Hurricane Hugo destroyed all of the oil storage tanks. The Hess oil refinery never fully recovered from Hurricane Hugo, and that refinery is no longer 800,000 barrels a day. It's a much smaller refinery, if it still exists at all. A lot of these structures, telecommunications masts, are procured from companies that sell them off the shelf, so to speak. They're standard towers. And you have to be very careful how you procure them. You must not assume that Rolls-Royce companies would always produce what you need in your particular facilities. A lot of the standard equipment in the UK has been designed for decades for 75-mile-per-hour winds. And this happens because in 1953, the first modern wind loading standard for the British Standards Institution was published, which had 75 miles per hour as the maximum wind speed. So a lot of these structures are inadequately procured. Be careful when you're procuring standard pieces of equipment. The owner of this house, an elderly lady, certainly could not afford insurance and didn't need insurance because her house, illustrated here, I photographed it 4 days after the Category 4 Hurricane Hugo devastated Montserrat with losses of 320% of the gross domestic product, and her house was completely intact. It had a beautifully shaped roof. It had hurricane shutters for the windows, and the doors were soundly fastened with hinges on one edge and bolts on the other. So you don't need a fortune to be safe. The 3 great churches on Church Street in St. George's, Grenada, were all destroyed by Hurricane Ivan in 2004. The Catholics repaired theirs soonest, followed by the Anglicans, but there were very few Presbyterians living in Grenada, and it took them a long time to get the funds to repair the Presbyterian kirk. But they had masonry walls which were destroyed by Ivan. The new, but not the present, National Stadium in Grenada was massively destroyed. The turnkey contractor was from Trinidad and Tobago, a very famous gentleman. And the design, detailing, and construction were pathetic. As you can see, this is how they detail the splices of the concrete columns to their bases. And can you imagine that this would happen in a hurricane? Can wind do this to reinforce concrete? It did. So any material can be sufficiently badly designed, detailed, and constructed and maintained to fail in a hurricane. Now, let's talk about something else which is not commonplace: the understanding of the dynamic wind effects on solar PV ground mount systems. On the 8th of October this year, I, along with a former vice president of APET, visited the largest solar PV ground-mounted installation anywhere in the Caribbean at Brechin Castle. Dynamic wind effects are crucial considerations in the design of solar PV structures, impacting their safety, efficiency, and longevity. The key effects include resonant vibrations, torsional galloping, and flutter. These phenomena can lead to severe structural damage if not properly mitigated. So understanding and designing for these effects ensures the resilience and stability of solar installations under damaging wind conditions. Don't take it for granted that they're going to be safe. This is St. Thomas in the US Virgin Islands in 2017. And this is the solar panels in Japan, a highly developed technological community, shattered by gusts in Isizaki, the Gunma prefecture in Japan. Flutter, which is aeroelastic instability in solar PV structures, is not unknown. So flutter is a complex phenomenon where aerodynamic forces cause a structure to oscillate in a potentially destructive manner. It typically occurs when the structure's natural frequency aligns with the aerodynamic forces, leading to energy input that sustains the oscillation. If you look very carefully, you can see some motions in the picture below. Let's go on. 2 months ago, I was visiting a friend in Maraval, Port of Spain. Maraval. And I could not believe my eyes because I saw demonstrated in the living room of my friend's home something I knew about, I read about, I studied, I understood from an academic standpoint, but I'd never seen it. And there I saw an example. Classic fluid structure interaction. When wind flows past a smooth cylindrical tower, it doesn't simply stream smoothly around it. Instead, you have boundary layer separation. As air flows around the curved surface, the boundary layer of air separates from the cylinder on each side. You have vortex shedding. The separated flow forms alternating swirling vortices behind the cylinder. You have alternating forces. Each vortex creates a low pressure region on that side of the tower. The vortices alternate from left to right. The tower experiences a side-to-side force perpendicular to the wind direction. So there you can see the wind is blowing at the BOP container on the table, but the BOP container is moving not in the direction of the wind, but at right angles to the wind. And you get vibration. If the frequency of these alternating forces matches the natural frequency of the tower, or the BOP container in this case, resonance occurs. So there is another view of the BOP, and there you can see it. It's moving from side to side. I did not do this deliberately. I was in the living room, the fan was on, there's a BOP on the table, and to my absolute shock, I saw demonstrated what I read about in textbooks, had to study for my exams, had to understand, had to deal with in design, but I had never seen it in practice. And there, all of a sudden, 2 months ago in Maraval, in the living room of a friend, I saw the phenomenon demonstrated. Before the wind blows, we have to insure properties, or some of us have to insure properties. And the insurance companies need to have some idea of how safe the structures are. So they ask consulting firms to produce fragility curves. Fragility curves predict what would happen to different forms of construction when the wind blows. Typically, the most fragile buildings are timber construction and steel frames with lightweight cladding. A bit less fragile are reinforced concrete with masonry walls and steel frames with infill masonry walls. And the least fragile if you have all reinforced concrete construction. So we produce fragility curves with greater or lesser degrees of accuracy for insurance companies, and they determine what premiums to charge you. And I personally have been blamed for the high premiums in the Caribbean because I have done many assignments for risk management solutions in California and for AIR Worldwide in Boston and for Guy Carpenter in London. And these are institutions that advise insurance companies of how risky it is to insure in different parts of the Caribbean. Sorry about that. Now, this is my last slide. And what it shows is that we have made tremendous progress over the past 100 years in reducing the loss of lives in hurricanes because we have much better warning systems now. We have satellite imagery, and a tremendous amount of research has been done. So we have much better warning systems. We can protect lives. However, those are the blue diagrams from 1900 to the year 2000. The green diagrams is property losses, and our property losses are skyrocketing. So although we are saving lives, we are losing buildings, we're losing structures. So we have, as engineers, a lot of work to do. Thank you very much.
Thank you, Engineer Gibbs. I am sure the audience is very much appreciative of the information that has been shared. It was a lot of info, detailed information to help persons make decisions with regards to wind design and understand the effects that you have been talking about. And I'm fairly certain that persons may have commentary or questions. So we'll now open the floor to those persons who would like to be able to pose a question to Engineer Gibbs with regards to the topics that will have been discussed this evening. Indicate.
Yes, I'm happy to answer. Is there someone moderating the discussion?
No questions at this time. I'm fairly certain. I found it very interesting that with the last slide, as you pointed out, that while we have reduced the number of deaths, that the cost of damages has gone up. Do you think that is related simply to the expansion of development, or is it combined with the fact that there is a combining factor of low quality construction alongside the level of expansion of urbanization?
It's one of the reasons. By the way, those two diagrams, really are not Caribbean diagrams. They're world diagrams, and mainly U.S. mainland data. And in the U.S., there's a tendency to move for development to go closer and closer to coastlines. People like to live, people are getting attracted to being close to coastlines. This is also happening in the Caribbean, of course. And coastlines are more vulnerable than inland areas. That's one thing. Other thing is that the building industry has become more highly competitive, and therefore people they have incentives to cut corners. When I was in the Bahamas after Hurricane Andrew in 1990, let's get it right, 1992, there was a place called Cat Key, which is a long, narrow island, a private island, and the development started on the southern end, and there was like the island was cut up like a sausage. So people started building at the southern end, and gradually from the 1934 to 1992, they had built all the way from the southern end, gradually up to the northern end. And if you, as I did, walked from the southern end to the northern end, there was very clear pattern. The older the buildings, the less damage there were. And that has to do with the marketplace and the competitiveness which has developed in the construction industry. But there is something else which bothers me significantly. The University of the West Indies has two faculties of engineering, two independent faculties of engineering, one in St. Augustine and one in Mona, Jamaica. Both faculties have departments of civil engineering, educating undergraduate civil engineers to practice in the Caribbean. Neither of those departments teach anything useful about wind forces on structures. I'm speaking from first-hand experience because I used to be the chair of the Industry Liaison Committee for the Civil Engineering Department at St. Augustine. And secondly, I've spoken as recently as in May last year, the APET conference, to the person who heads the Civil Engineering Department in Mona. In neither case are wind forces and structures being taught in anything like a normal academic manner. Effectively, it's not being taught at all. So that's an awful situation which we face in the Caribbean. So a hazard which is prevalent in the Caribbean is not being addressed adequately by the major English-speaking university in the Caribbean.
I appreciate your sentiments. That's something definitely to be addressed. I can say from my own experience, there was a lot of focus on structures, in particular seismic impact. So I will confess, wind was not a high topic, and I expect it probably still is the case. In terms of the damage you will have shared, that particular scene where the longitudinal failure of the timber rafter, just to be clear, the rod that you will have spoken about that was bored through the rafter will have been horizontal through the rafter. And
yes.
Then, right, so it will have threaded its way through all of the rafters, and that would have been the point of failure for the share.
Yes.
That's interesting.
That's where the damage initiated. Yeah.
It's a long-standing, that method is a long-standing one where the rafter is set into the block and essentially cast in place with that rod. That's a long-standing method, but that turns out to be a failing item. And more interesting to me is that the roof cover appears to be asphalt shingles, right? That then led to that type of failure.
Well, the whole roof, the whole plywood sheeting came off, of course. Came off with the top halves of the rafters. Yes. Yeah.
Yeah, that was eye-opening because I know discussions within the Caribbean region, you hear persons talk about that approach and that method as an absolute one that is definitively safe. And here we see pictures
Well,
that it isn't.
well, I thought it was a very safe method until I went to Montserrat in 1989.
Yeah, yeah. But
I
that lesson is not widespread.
Yes,
It's still exported as the as one of the methods to utilize. Similarly, in
yes,
Trinidad and Tobago, where steel frames dominate the landscape for residential roofing, the methodology that is used is to anchor steel into our concrete ring beam and sort of weld it off. And I think that in recent wind events we had locally, there were examples where that method has shown itself to fail to anchor those roofs in place when in the type of wind event that an extreme wind events. So it begins to showcase that the methods that are being used typically on the landscape are not as safe as people think that they are. And it begs to wonder if we need to try to put more information into the public landscape.
yeah. There's a lot of work to be done, quite frankly, quite a lot of work to be done. Um, but it's the work to be done is not. We don't need more information. There's nothing wrong with continuing research and continuing to increase our knowledge of the phenomenon. But we have enough information already to produce safe buildings, safe structures. We're just not using the information.
Right, application
Yeah.
linked with good execution.
Yeah.
So once again, if
And
anybody has any questions, commentary, feel free to unmute. If you're having problems, just put your hand up. We'll try to help you out with
now,
that item.
towards the end of my talk, I did bring in this matter of photovoltaic, solar, ground-mounted systems. Those of you who went to the APET conference in May last year at the Hyatt, I gave a talk on the vulnerability of those systems. There's a lot that is not understood about that system. We have a situation in Barbados where the government's aim is for, by 2035, 70% of our power in Barbados will be by the sun, most of which would be on ground-mounted photovoltaic solar systems. And there is very little, very inadequate understanding of the vulnerability of those systems in the government of Barbados. Very little understanding. And so what the Barbados Chamber of Commerce and Industry is at the moment trying to do is they've already put together a panel to produce information and to go to stakeholders, not only government, but in fact, mainly not government, to sensitize the entire population with the need to pay better attention to the safety of those systems. Because those systems, there are various vulnerabilities to various different hazards, not only the wind. And it's not only the strong winds that can destroy them, it's also very low wind speeds, such as you would very commonly get in Trinidad. Because if those structures, many of them have very low natural frequencies. And if you have a structure where the natural frequency is low, you're looking for trouble, even with light winds.
Yeah, I think that's deeply appreciated. That Brechin Castle installation was a topic of presentation by the Electrical Division and of APEP just last month. It was an informative item showcasing the construction approach, methods used, and that was one of the questions that did come up. Now, at this time, I can't recall what was the nature of the wind speed that they used, but some considerations for wind was covered in their design. But I'll definitely be sure to reach out to our friends in electrical division to reinforce that item, since we know that they have a role with that installation in Brechin Castle.
They need to be designed for maximum wind speeds, such as hurricane winds, and they also need to be designed for low wind speeds. And the analysis for low wind speeds is a dynamic analysis. And if I go back to UWI again, I'm sorry about that. In 1995, I was on the joint board of moderators doing an assessment of the BSc in civil engineering at St. Augustine. In 1995, at the debriefing, when we did give them the all clear for the degree at professional level, which they no longer have. We did tell them that they must make dynamic analysis a mandatory course in undergraduate studies with sufficient detail that the undergraduates, when they graduate, can actually do dynamic analysis, because there's no civil engineering structure anywhere in the Caribbean that's not impacted by the dynamic loading, either earthquake or wind or waves. It's all dynamic loading. And up to now, St. Augustine does not teach enough dynamic analysis, and dynamic analysis is required for those solar PV ground-mounted systems, is required.
I appreciate your input on that matter. So before we close up, one last offer to our audience in terms of any questions they may want to ask. Again, we know we had a lot of content. If persons are interested, the floor is open. If not, I will then proceed to thank Engineer Gibbs for the time he has taken to share his expertise, his knowledge, his experience with us for this evening. It is well appreciated, especially with the examples, small and large, that demonstrate the effects of wind and how simple measures can be taken to ensure security and resilience to the structures that we utilize and inhabit on a daily basis. Thank you, Engineer Gibbs, very much joining us from Barbados. It is always a pleasure, and we look forward to having you again in any function.
And thank you very much for inviting me. I'm always happy to well, you know, I'm 88 years old, and my main job now is to empty my mind and into other people's minds.
So, and we appreciate that very much.
Yeah.
So,
okay.
If we don't speak again, safe trip to see the Sydney Opera House.
Yes, I'm going to see the Sydney Opera House, and then I'm going to see the Boxing Day Test match in Melbourne.
I'm sure it will be a wonderful event. Sounds like a very well-planned trip.
It's England versus Australia, and the English team includes, unfortunately, the best West Indian batsman at the moment. His name is Bethel, and the best West Indian bowler at the moment, his name is Archer. And they're playing for them, not for us.
I hear you. Yeah. All right, and with that, couple comments, very informative as expected, and kudos for an excellent presentation. And with that, we thank you again, and we ask everyone to get home safely for those of you who are still on the way home, and for those at home, do rest well. Thanks again, and good evening.
Thank you. Good night.